Okay, first I want to thank Scott and Justin and all of you for inviting us here. We have a rather unorthodox talk, I suppose. At nearly the same time Joe and I learned we were accepted to the symposium, the winter 2014 issue of RSQ hit my mailbox. It included a review by G. Mitchell Reyes, in which he petitioned for more rhetorical studies of mathematics. The fields of rhetoric and mathematics, Reyes claims, have an inherent kinship. He argues that the, quote, meaning and significance of a mathematical statement comes not from its infallibility, but from its metacode. Therefore, he continues, the context of mathematical concepts is crucial to understanding their fascinating, evolving, contextually situated, creative practice of reading and writing. A tempting call to investigating inventive practices of a field quite different from my own. The hazard here is that if rhetoricians focus on the metacode driving mathematics, we may become too engaged in unearthing the hidden from beneath others' fields. And such criticism does have value, as we've seen today. Liz Losh's talk last night about hashtags showed some of the potential of such archaeology, particularly outside a United States context. And S.D. Beck just now has continued that conversation. Approaching coding from a rhetorical perspective, we can use our investment in coding as a way to build disciplinary bridges with mathematics. As Losh pointed out in her book, Virtual Politic, quote, the discourses of computer scientists themselves, however, tend to be conspicuously absent from scholarly books and articles about digital rhetoric. Her approach to co-evolving demands that contemporary rhetoricians have at least a basic understanding of technology theories in order to do digital rhetoric. Fair enough. But my concern when working with mathematics is that I'm unlikely to be skilled enough in that discipline in order to do it justice, although Bill has shown that it is very possible. Yet, as this and other panels this weekend show, mathematics is the basis of much computer programming and development. And as Losh says, we are, quote, wearing blinders if we ignore such disciplines. Hence, rather than setting math aside as inaccessible or non-rhetorical, and rather than trying to reach fluency in a vastly unfamiliar disciplinary language, we have created here, Joe and I, a partnership. We work together, not for me to find the, quote, secrets of mathematics, but to test rhetorical conceptions of invention and engage in productive dialogue for both fields, as Crystal Van Coten pointed out in her categorization of our work this morning. To do this, we chose a specific text, linear programming, which is the foundational logic undergirding much of mathematical modeling, and hence has a direct relationship to the technoscientific concerns of many of our presenters at this symposium.
Although the term is rarely heard outside of mathematics, linear programming has applications almost everywhere. Many of the algorithms mentioned by our most recent speaker are implemented using linear programming. Linear programming was designed for, and it's very good for, studying systems in the real world over which humans have influence or control. I will now explain what linear programming is in an intuitive, that is to say, a not mathematically rigorous way. The first thing I will say is that a linear program is not a type of computer program. It so happens, confusingly, that we usually use computer programs to work with linear programs, a topic that Jennifer and I will discuss soon. However, the term program in linear programming has a different origin. When linear programs were first studied in the 1940s, the term programming was used by the US military to designate planning problems. The methods that mathematicians developed to solve planning problems were collectively called mathematical programming, and one type of mathematical programming is linear programming. Linear programming is an activity. The things you create when you engage in that activity are called linear programs. So we are now basking in the presence of a linear program. As with most mathematical objects, there are several different ways to represent a linear program. So on the screen, we have two equivalent representations of the same linear program. This is a program that I made up for the purposes of this presentation, which I will refer to as our toy problem. It represents a pasta factory. So in our pasta factory, you can make two types of pasta, lasagna, and macaroni. They both use the same ingredients, but it takes longer to make macaroni because you have to bend them. However, you can sell the macaroni for more. You want to use this linear program to create a production plan that yields the maximum profit. So first, I want to talk about the algebraic representation of this linear program. The statement at the top is called the objective or objective function. it expresses your objective for this system, to have the maximum profit. The numbers in that objective function represent how much you can sell the different types of pasta for. Below the objective, we have the constraints. These are the rules that you have to follow in order to make pasta. So here we have 4 constraints. The first one is about the available ingredients. The second one is about the hours of available labor. And the last 2 say that you can't make a negative amount of pasta. So some of those are very easy to convince people of. There are a lot of other constraints that we could add to describe a pasta factory, but I'm limiting us to these few because this is a toy problem. In practice, choosing the objective function and constraints for an application, which we call modeling, is often just as difficult as the mathematics of solving the program we create. We recognize that we can't describe everything mathematically, but we try to describe enough so that our solution will help the decision maker. There's an often repeated quote from the statistician George E.P. Box about this process. Essentially, all models are wrong, but some are useful.
I love that quote. Every time he says it, I love that quote. What can rhetorical critique do with such a toy problem? Well, one option is to access the variables and constraints of the model so we can analyze which factors are being considered and which aren't. What do these considerations reveal about the values, purposes, or identity of the mathematics and the resulting meta code? This model, as Joe says, is a simplification. What it doesn't account for, among many other factors, is randomness and demand. What I originally wanted to assume was that if I could identify the constraints in his model, such as randomness and demand not being there, I would know more about what a mathematician valued or thought was significant. Currently, this toy problem assumes you can sell his pasta for a single price, that people will buy it, and that they will always buy it. As wonderful as I'm sure it is, this is unrealistic. What I learned was that this analysis of constraints is not always as revealing as a rhetorician would hope. There are some constraints that simply cannot be expressed as a linear program. Mathematicians may have to make concessions or fudgy math. That's a term I had approved by him. Fudgy math to work with the model. Ideally, a team of mathematicians working together to build the model will consider these constraints carefully, negotiating between the requirements of the problem, the processing capabilities of the computer, and the restriction of preferring to express the problem linearly. That negotiation means that from a rhetorical standpoint, just understanding the constraints is insufficient if we want to understand the way mathematics creates. What I've learned is that mathematicians find optimal solutions to a mathematical representation, a mathematical story about a given system.
So you may have noticed that Jennifer said solutions instead of solution. I realize this may contradict your prior experience of mathematics, in which there was usually only one solution to a problem and you were tasked with finding it. But for a linear program, there are many solutions. In the context of linear programming, a solution is any set of decisions that satisfies the constraints. So if you think about our imaginary pasta factory, there are a lot of different and legitimate ways to run a pasta factory. You could make half lasagna and half macaroni. That is a solution. Or you could go the pure lasagna route, only lasagna. That is a solution. You could even choose to make no pasta at all. Now, that's obviously a terrible idea, but it doesn't violate any of the constraints, so that is also a solution. All the possible solutions are summarized in the geometric representation of the linear program. So if you could please fix your gaze on the geometric representation, this graph, it is equivalent to the algebraic representation. We have 2 axes. The axis labeled X is our lasagna axis, and the axis labeled Y is our macaroni axis. Each of the lines in the graph corresponds to one of the constraints in the algebraic representation. So if you were to solve those constraints for a single variable, you would get these lines. The shape bounded by the lines is what we call the feasible region or the solution space. It contains all of the possible solutions to our linear program, all the different ways that you can run this pasta factory. When we solve a linear program, it means that we explore the feasible region until we find one of the best solutions. Our technical term for that is an optimal solution. And note, I say one of the best because there could be a tie, although for this problem there isn't. An optimal solution is determined by the objective. So in our graph, the objective is represented by this small vector, this little arrow, and it shows us which direction we should move in the feasible region in order to find the optimal solution. And for this linear program, the unique optimal solution is to produce I wrote this down because I know it's important. You want to go do this later. 12 units of lasagna and 18 units of macaroni. It's right there at the point.
You solved it. This process Joe described shows, to me, openness to contingency or possibilities. Reyes points out that Aristotle often used math as an example in his rhetoric. In fact, Aristotle mentions math when he discusses the possible and the impossible. When giving an example of impossibility, he says, quote, "The commensurability of the diagonal of a square with its side neither occurs nor can begin to occur." So this is impossible, as you can see here. The diagonal of a square simply cannot be commensurable with a side. Now, this is geometry rather than algorithm development, of course, but I can see the appeal of using math at this point in Aristotle's argument. Math seems so very definite, so true or false here. Aristotle doesn't necessarily accept that math can be contingent, can have multiple solutions, as Joe describes. In fact, he doesn't use math as an example of the possible at all. He uses it as an example of the impossible. The rules of math are set according to his example, a common assumption by many who work on math but are not in the field itself. Another assumption we can trace to Aristotle is from the Nicomachean Ethics, in which he implies that mathematics is episteme, not techne. Hence, math is made of necessity rather than being an art. What Joe's example shows is that it is also techne. The solutions could be otherwise. By reconsidering mathematics as techne, we can view it as a form of making, of creating, and as Esti has argued, it can therefore be persuasive.
To show how we do the kind of creating that Jennifer is talking about, I will describe how we actually solve linear programs in practice. That is how we find the optimal solutions that we're looking for. Very early in research about linear programming, an algorithm was developed called the Simplex Method. This is a systematic way of exploring the feasible region and finding the optimal solution. Mathematicians discovered very early that one of the optimal solutions for a linear program lies at these points on the edge of the feasible region where two lines intersect. So the Simplex Method works like this. It starts at any one of those intersections, and then it moves from there to a neighboring intersection in a systematic way until it gets to an optimal solution, and then it stops. It's like a bug crawling around the outside of the feasible region, always moving towards somewhere warmer until it can't move again without becoming colder. So on our toy problem here, this seems like a waste of time because, implementing the Simplex Method would be silly. You have the vector to represent the objective function. It is right there. It is pointing at the optimal solution. But this is a linear program with two variables. So it's in two-dimensional space, and we can look at it on this two-dimensional surface. In practice, most problems have many more variables. I often work with problems that have hundreds of thousands of variables. So instead of this nice quadrilateral, the feasible region is some kind of exotic shape that I can't even begin to imagine. By using the Simplex Method, that exotic shape can be explored as easily as this two-dimensional shape. However, in order to do so, we have to use matrices. So this is another representation of our linear program, the matrix representation. A matrix is a collection of numbers organized into rows and columns. So I'm not going to explain exactly how you turn our algebraic formulation into this set of matrices. I'm just going to point out that the same numbers appear in kind of similar places in both of them. In order to use the Simplex Method to solve a linear program, you perform a series of repetitive calculations with this set of matrices. In the very early days, when computers were rare, people actually did this by hand. Later, they programmed computers to do the repetitive calculations. But they still worked with linear programming, primarily thinking of matrices. Because when you're using the Simplex Method, some matrices can be solved much more quickly than others. So computers were very slow. They had such a small amount of memory that efficiency was the difference between solving your linear program and having the computer crash with no solution at all. At every step of working with a linear program, the practitioners were conscious of the need to create types of matrices that could be solved efficiently.
His statement that we are going to explore the feasible region until we find one of the best solutions is striking to me. This is invention. It's a search for the best topoi, the best approaches to navigate the current situation. But the variables and the processes, as he said, become so many and so complex that they are impossible for a single individual to assess. Rather, the math researcher collaborates with a computer, a number cruncher. Reyes argues that, quote, a turn to mathematical discourse challenges critical affinities. Math, as Latour suggests, weaves networks of humans and non-humans into ever more complex collectives. To attend to mathematical discourse on its own terms then requires us to transgress the borders of humanism so that we can incorporate non-humans into our analyses. End quote. It's only reasonable to assume that math researchers have become increasingly dependent on and adept with creating their programs in order to have them calculated via computer. That is, as Reyes contends, one mode of human and non-human co-invention. The researcher cannot solve the problem alone. Sorry.
Let's talk more about that last statement. So, although I might be so brazen as to say the words, I'll solve this linear program, I almost never write out a matrix or draw a graph of a feasible region, or even imagine a feasible region in some cases. Much less do I actually go through and explore solutions on my own. That work is performed by a friendly computer program called a solver that implements an algorithm like the Simplex Method. I can direct or influence the process used by the solver, but the solver is the agent that actually obtains the optimal solution for me. So I interact with solvers by using what we call modeling languages. And here, going back to our toy problem, we have the algebraic representation with the objective and constraints. Next to it, we actually have exactly the same information, but written in a modeling language called AMPL. This isn't a different representation of the linear program. This is just written in a different way that a computer can interpret. The algebraic representation of a linear program is mostly useful as a communication tool. That's why I started from it and why I've continued to work from it when I'm explaining these different representations to you. But only the matrix representation can be used to solve linear programs with more than a few variables. This modeling language translates my algebraic representation into a matrix representation and then sends that to the solver, which attempts to solve the linear program for me. My role in this process is to use algebra and my knowledge of the system being modeled to find the best way to solve the underlying problem with the solvers available to me. Now, presently, some researchers are developing what are referred to collectively as meta-modeling languages. These are languages that add a layer between the practitioner and the modeling language that annex a part of my current role. When I described these to Jennifer, she proposed that this is an example of the process of accretion, as described by rhetorician Kenneth Burke.
Well, I think it's a form of accretion because even though these meta-modeling languages further enable the co-inventional process between the computer and the researcher, you've told me there could be problems as well. After all, this invention is taking place layers up from the base linear program. The original layer, the linear program itself, is being subsumed. True, this accretion improves efficiency, but it can also disguise certain undercurrents. From our dialogue, I've become ever more aware of mathematical rhetoricity, not just in terms of accretion, but also in terms of the overall inventional process for mathematicians. As Joe has just described, part of his work involves creating multiple languages. One to communicate with humans, which often involves algebraic representation and metaphor, and another language to communicate with his non-human partners. Digital rhetoric, as described by Losch, has made inroads into certain kinds of mathematic and computer relationships, such as data storage, web development, digitization practices, software studies. Virginia Kuhn and many of you here are doing good work in this field. But perhaps we could also move forward by working with those in the field of mathematics, not by imposing our terms on them, but by working through deliberative dialogue to identify bridges on which our fields can meet and reach understanding. Working with Joe on this does not mean that I can now do fluent mathematical research, as Bill can. But it does mean that we can better understand mathematicians' processes, their choices, their rhetoric, and how their use of rhetoric helps craft our world.